Hi students, good morning everybody. In this video, we are going to see about electric energy and electric power. That is energy and power in an electric circuits. When a battery is connected between the ends of a conductor, you all know that a current is established in the conductor. The battery is supplying energy to the device which is connected in the circuit. Consider a circuit as shown in the diagram having a battery of voltage V connected across the resistance R. Consider a positive charge of dq moves from the point A to B through the battery and moves from the point C to D through the resistor back and then to the back to the point A. So a charge is a positive charge is moving from A to B across the battery and from C to D across the resistor, and finally the positive charge is reaching the end A. So when the charge moves from point A to B, what it does or what is it doing? It gains potential energy from the battery, and the chemical potential energy in the battery is given to the charge that is moving across the potential difference from A to B. When the charge dq passes through the resistor, once again the charge loses the potential energy it has already gained to the resistor. So here du, which is the change in the potential energy, is equal to V into dq, where V is the potential difference across which the charge is moving and dq is the charge. And due to the collisions with the atoms in the resistor, the charge is losing its potential energy and again reaches at the point A. During the process, the charge, this process occurs continuously in the circuit till the battery is connected in the circuit. The rate at which the charge loses its electrical potential energy in the resistor can be calculated. The electric power is the rate at which the electrical potential energy is delivered. Okay, so P is equal to work done by time taken. Instead of work, I can write du by dt. You know that u is nothing but V, so du is nothing but V into dq. So P, electric power, is equal to V into dq by dt. But you all know that dq by dt is nothing but current I. So P is equal to V into dq by dt, which is equal to P into I. The electric power P is equal to V into I. This expression gives the power delivered by the battery to any electrical system, where I is the current passing through the device and V is the potential difference across it. The SI unit of electric power is watt, and 1 watt is also equal to 1 joule per second, because power is equal to work done by time taken. So 1 watt is equal to 1 joule per second. Commercially, if you see the electric bulbs we are buying from our shops for houses, you can able to see the power and the voltage ratings in the bulbs like this: 5 watt 220 volt, 30 watt 220 volt, 60 watt 220 volt, like this. This diagram shows the electric bulbs with the power rating. Usually the voltage rating refers to the AC RMS voltages, or root mean square voltages. For a given bulb, if the voltage drop across the bulb is greater than the voltage rating, the bulb will get fused. Using Ohm's law, power delivered to the resistance R is expressed in other forms. P is equal to VI. Instead of V, substitute IR. So P is equal to I into IR, which is equal to I square R. And instead of I, substitute V by R. So P is equal to IV is equal to V by R into V is equal to V square by R. So there are three expressions for power in an electrical circuit. One is P is equal to VI, the next one is P is equal to I square R, and the next one is P is equal to V square by R. These three equations are very important equations to be remembered. The next one is The total electrical energy used by any electrical device in our house is obtained by multiplying the power and the duration of time. That is, total electrical energy E is equal to power into time. Power is expressed in watts and time is expressed in seconds. Then electrical energy is equal to watt second or watt hour. In practice, in our daily practical life, the electrical energy consumed by us is measured in what is called as a unit. What is 1 unit is equal to? 1 unit is equal to 1 kilowatt hour. 1 kilowatt hour is the practical unit of electrical energy, or which is equal to 1 unit. 1 kilowatt hour is equal to 1000 watt hour, which is equal to 1000 watt into 3600 seconds, which is equal to 3.6 into 10 power 6 joule. So 1 kilowatt hour is equal to 1 unit is the practical unit of electrical energy used by us, and 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. This is a very important expression. The next topic is electrical cells and batteries. What is an electric cell? An electric cell is a device which converts chemical energy into electrical energy to produce electricity. In a simple electric cell, it consists of two electrodes. One is a carbon electrode and another one is a zinc electrode placed in an electrolytic solution, for example sulfuric acid. When several electrical cells are connected together, it forms a battery. When a cell or a battery is connected in a circuit, what happens means electrons flow from the negative terminal of the cell or a battery to the positive terminal through the circuit. By using chemical reactions, a battery produces a potential difference which is useful for the electrons to move from one part of the circuit to the another part of the circuit. This is the diagram of a simple electrical cell which consists of electrolyte, this dilute sulfuric acid. This is a carbon electrode which is the positive terminal, and this is the zinc electrode which is the negative terminal. When the cell is constructed like this, the chemical reactions produces potential difference across its terminals. This potential difference provides the energy to move the electrons through the circuit. This diagram shows the commercially available electrical cells and batteries. Next, we are going to see an important part which is the electromotive force and internal resistance. A cell or a battery is a source of electromotive force. By the term electromotive force, you does not misunderstand that it is a force. Actually, electromotive force is not a force, but it describes the potential difference between the two terminals of a cell or a battery in volt. So, yeah, the electromotive force does not refer to force. The EMF of a battery or a cell is the voltage provided by the battery when no current flows in the external circuit. Electromotive force determines the amount of work done by a battery or a cell to move a certain amount of charge around the circuit. Electromotive force is or EMF is denoted by this symbol. Usually see the symbol I am showing it here represents the electromotive force. An ideal battery has zero internal resistance and the potential difference, that is across the two terminals, terminal voltage across the battery equal to its EMF. But in reality, the battery is made up of electrodes and electrolyte. There is a resistance to the flow of charge within the battery. This resistance is offered by the electrolyte. This resistance is called as the internal resistance, small r. For a real battery, the terminal voltage is not equal to the EMF of the battery. A freshly prepared cell has a low internal resistance and it increases with aging. So for any battery or a cell, there is an EMF or an electromotive force which is represented by these letters E, and there is an internal internal resistance R. The next topic we are going to see how we are going to determine the internal resistance of a cell using voltmeter. These two diagrams represents the diagrams used for the determination of internal resistance of a cell using voltmeter. Let us consider the first diagram. This is a cell or a battery of EM of E, and this represents positive terminal, this represents the negative terminal. A voltmeter is connected across this EM of cell in this way, and so the circuit represents the circuit formed for internal resistance. You all know that a voltmeter is a device which is used to measure the potential difference across the two ends. A voltmeter has a high resistance actually. So when this circuit is connected, what happens means a current will flow through the circuit, and now the cell is connected in this manner is said to be in the open circuit because no external resistance is connected here. In the part R small r shown in this diagram represents the internal resistance of this cell having an EM of E. So when this connection is made like this, the voltmeter will show a reading. The reading shown by the voltmeter is represents the EMF, indicates the EMF of the cell. Now you take an external resistance R and connect it in the circuit, included it in the circuit, and connect the voltmeter across this external resistance. See, now listen carefully. Small r represents the internal resistance and capital R represents the external resistance. Now the circuit is said to be in the closed circuit. Because of the closed circuit, a current I will flow through this circuit. When a current I flows through this circuit, it flows through the external resistance R also. There will be a potential difference developed across the external resistance R, and it is given as V is equal to IR. Now the voltmeter will show some reading. The reading shown by the voltmeter now will not be the same as the reading shown by the voltmeter in the previous case when no external resistance is connected. Why? What is the reason? Due to the internal resistance R of the cell, the voltmeter now reads a value V which is less than the EMF of the cell. It is because certain amount of voltage IR has been dropped across the internal resistance. Because of this reason, the reading shown by the voltmeter now will be less than the original EMF, original reading. So I can write V is equal to E minus IR since there is a potential drop across the internal resistance. So this above equation can be rewritten as IR is equal to E minus V. Now you divide this equation by this equation, we will get IR by R is equal to E minus V by V. I get cancelled, so R is equal to E minus V by V into R. This formula helps us to calculate the internal resistance of the cell. Here capital R represents the external resistance used, capital E represents the reading shown by the voltmeter when no external resistance is connected, and capital V represents the reading shown by the voltmeter when an external resistance is connected. So the internal resistance of the cell can be calculated using the formula R is equal to E minus V by V into R. Since E, V and R are known, internal resistance of the cell can be determined. Now we can also find the total current that flows in the circuit. Due to the internal resistance, the power delivered to the circuit is not equal to the power rating mentioned in the battery. For a battery of EMF E with an internal resistance R, the power delivered to the circuit of resistance R is given as P is equal to I into E. Instead of E, we can substitute V plus IR. So P is equal to I into V plus IR, where V is the voltage drop across the resistance and it is equal to IR. So the above equation now will become P is equal to I into IR plus IR, where capital R represents the external resistance and small r represents the internal resistance. So when you expand this, we will write P is equal to I square R plus I square R, where I square small r is the power delivered to the internal resistance and I square capital R is the power delivered to the electrical device. Here it is resistance R. For a good battery, the internal resistance R is very small, then I square R, the second term, is very smaller than I square capital R, and almost in this case entire power of the battery is delivered to the external resistance. Now we can see the connection of cells in series and parallel. First of all, cells in series. Several cells can be connected to form a battery. If a number of cells are connected in series connection, if you see in this figure, the negative terminal of the first cell is connected to the positive terminal of the second cell. The negative terminal of the second cell is connected to the positive terminal of the third cell, and the negative terminal of the third cell is connected to the positive terminal of the fourth cell, and the negative terminal of the fourth cell forms one end and the positive terminal of the first cell forms one end. These two ends are connected to an external resistance, or here the internal resistance of all these four cells is represented as small r, and the EMF of all these four cells is represented by the symbol E. Now suppose if n number of cells are connected, each of EMF E volt and internal resistance R ohms are connected in series with an external resistance, and in this case let us see what will happen to the current in the circuit. This is a very important derivation. Since the cells are connected in series, the total EMF of the battery is equal to N into E, where N represents the number of cells and E represents the EMF of a single cell, all having the same value. The total resistance in the circuit is NR plus R, because all the N resistances, N cells are connected in series, and each one is having R as the internal resistance. So total resistance in the circuit is equal to NR plus R. So by Ohm's law, the current that is flowing in this circuit, I is equal to total EMF by total resistance, which is equal to NE by NR plus R. This is a very important equation. Using this equation, we can discuss two cases. Case 1, suppose if the internal resistance R of a cell is very far less than the external resistance, then what will happen? This term NR can be neglected, because the value of R is very far lesser than capital R. The term NR in this equation can be neglected. So the above equation will become I is equal to NE by R. What is E by R? E by R represents the current due to a single cell. So I can write I is equal to NI1, where I1 is equal to E by R. Thus, therefore, it is clear that if R is negligible when compared to the external resistance, the current supplied by the battery is n times than that of supplied by a single cell. So in this case, when internal resistance is very smaller than the external resistance, the current supplied by the battery increases. But in the second case, if R is far greater than capital R, if the external resistance happens to be greater, if the internal resistance is greater than the external resistance, then the term, this term can be, capital R can be neglected. So the above term will become NE by NR. So N and N will get cancelled. So I is equal to E by R. It is clear that the current due to a single cell, that is current due to the whole battery is the same as that due to a single cells, and hence there is no advantage in connecting several cells if in series if the internal resistance is greater than the external resistance. So the series connection of cells is advantageous only when the effective internal resistance of the cells is negligibly small compared to the external resistance. Next we will see about cells in parallel. The diagram shows the number of cells of having CM of E connected, having same EMF, having same internal resistance connected parallel. That is, all the positive terminals of the cells are connected to one end and all the negative terminals are connected to the other end, so that this positive terminal forms the positive terminal of the battery formed, and this represents the negative terminal of the battery formed, and these two ends are connected to the external resistance capital R. Now all the cells are connected in parallel, and each cell is having an internal resistance small r, and each cell is having the same value of EM of E. Now as all the cells are connected, all the internal resistances are connected in parallel, the equivalent internal resistance of the battery is 1 by R equivalent is equal to 1 by R plus 1 by R plus etc up to 1 by R, that is n terms, which is equal to n by R. So R equivalent is equal to R by N, and the total resistance in the circuit is this R by N is in series with the external resistance. So the total resistance in the circuit is equal to R plus R by N, where capital R represents the external resistance. Therefore, the total EMF is the potential difference between the points A and B. Therefore, the current in the circuit is given by I is equal to E by R by N plus R, which is equal to NE. If you simplify this, we will get I is equal to NE by R plus NR. This equation is different from that of the previous case. Okay, so let us, using this equation, let us consider the cases. Case 1, suppose if the internal resistance is far greater than the external resistance, that is R is very far greater than capital R, what will happen? NR, the second term will get cancelled, so you will get I is equal to NE by R, which is equal to N into I1, where I1 is the current due to a single cell E by R when R is negligible. Thus the current through the external resistance due to the whole battery is N times the current due to a single cell. Suppose if R is smaller than capital R, that is, if the internal resistance is less than capital R, then I is equal to E by R. When I is equal to E by R means the current in the external so the external resistance due to the battery is equal to the current due to the single cell. So in this case, when the cells are connected in parallel, it is advantageous only when the only if the internal resistance is far greater than the external resistance. It is just opposite to the case of the cells connected in series. Okay girls, thank you.